So section 2.5 is going to discuss linear models. And of course, a natural place to discuss linear models is to begin by talking about roller coasters. Now, what's the coolest thing about being on a roller coaster? The thrill, scare, especially that initial hill, right? When you start going really, really fast. Now, this is a cool data set that discusses all the attributes of almost all the coasters in the United States. It's got all kinds of great statistics: top speed, max drop, length, duration, type, year built, city, everything you could want. But let's focus on the fun part, right? And the fun part, of course, would be the maximum speed, how fast you get going. So here's our data. And it's kind of cool when you're working with this because you can poke around and find, for instance, my favorite top fuel dragster at Cedar Point, 120 miles an hour. And it should highlight that point in the data sets here someplace. Let's try again. There it is right there. Now we can keep an eye on that as we drag over top speed to the y-axis. That's going to be our response variable. Okay, so that organizes things a little bit. But what we want to do is we want to predict the top speed. What's going to tell you the top speed? So I'm thinking that drop on that initial hill. So let's drag that over the x-axis. That's our x variable. And wow, the data seems to organize itself into kind of a line. And that's what we're going to work on in this section, is figuring out, linear models. So let's start by recalling a few things about linear equations. Quite often we write them in this form: y equals mx plus b. I hope you remember a few things about these things. Of course, m is for the slope. And a lot of times we'll have to calculate that based on a couple points of data. So y2 minus y1 over x2 minus x1. And b is the y-intercept. This is where it crosses the y-axis. So with those two things, let's take a look at some examples. We'll start with example A here. And it might show up a little bit better if I look over here. So that might be a little bit easier to read, at least initially. It says a swimming pool is being filled. The graph shows the number of gallons in the pool after X minutes. Of course, the question is, what's the rate of change, or how fast is this pool being filled? So, okay, let's figure that out. Now, the rate of change for us is going to be the slope. And there's a couple ways we can work on the slope. So one way is to actually come up with a couple points. So here's 1 point. And we don't have to go very far to get another one. There's another point. Now, based on what's going on here, each one of these tick marks is worth 10 units. So this is up here at 30. And of course, we've got 2 points, 0 and 10, and 1 and 30. So if we put that into our slope formula, x1, y1, x2, y2, we can come up with an equation, or excuse me, we can come up with a slope. So it'd be 30 minus 10 over 1 minus 0. The big thing about using this formula is you have to be consistent. If you're subtracting this way, 30 minus 10 in the numerator, then it has to be 1 minus 0 in the denominator. So that would give you 20 over 1, or a slope of 20. Alternately, you don't have to really be that careful about which way you subtract, as long as you're consistent in the numerator and denominator. If you would have done 10 minus 30 in the numerator, that means you have to do 0 minus 1 in the denominator. It works out to the same thing. You just end up with an extra set of negative signs that cancel each other out. So no big deal. Now, the other way we can work on this is to remember something about what slope represents. Slope represents the rise over the run. So Let me see if I can't squeeze it in someplace. Let's see. M equals rise over the run. And the run is this distance. It's your horizontal distance. So that's a distance of 1. And the rise is the vertical distance. And that distance is 20. So without necessarily getting fancy and writing down all the points, you can come up with the slope that way. And that's the rate of change of this graph. Nice. So kind of a good little warm-up example. Let's move on to a couple more here. This should be hopefully a relatively easy section for us. Let's keep going with example B. So let me zoom out a little bit here. Let's try it again. There we go. And I'll come over here and look at example B. Basically, it's to determine whether given functions are linear or not. So if they're linear, then you can write them in the form that we wrote them in earlier. That is y equals mx plus b. Kind of like this. So for example B, our function is f of x is 8 minus 3x. That's not quite in this form yet, but we can simply move things around a little bit to turn into that form. If we change things around, write that as y equals negative 3x plus 8, now we're in good shape. One of the big things that I see people making a mistake on is saying the slope is negative 3x. No, it's just the coefficient. That's our slope. That's our y-intercept. In fact, let's take a quick look at that on Desmos. So that would be up here. And here's your graph. Now, if you're looking at this on Desmos, you can make this a little bit nicer to look at. If you go to the tool icon and click the capital letter A, it just makes it a little bit easier to see. We can see a couple things that we expected. We expected, for instance, a y-intercept of 8. Okay. If you click this graph right here on the y-axis, 0, 8, there's your y-intercept. Here's your x-intercept. It's actually given to you as a decimal, not a nice fraction, but that's okay. You can, from this, figure out the actual slope if you wanted to, just by doing rise over run. There's a rise of a negative 8 and a run of 2 2/3. So you can form a ratio and come up with a slope that way. We don't need to. We can just read off the slope right here. Let's take a look at a couple others in this series here. They're all part of example B. The next one is to determine whether or not this function is linear. So f of x in this case is x times 3 minus x. If I distribute that x, I get 3x minus x squared. And once you start seeing an exponent here, something other than a 1, it's no longer a linear model. In fact, this is a quadratic equation, quadratic function, I should say. It's not going to be a nice straight line. So if I shut this off and turn this one on, you see a parabola, which is not a big surprise, I hope. Finally, the last one is f of x is x plus 1 over 3. Well, all I see is of x to the first power, so it could be linear. If we wanted to put it into this form, then here's what we could do. You could write this as x over 3 plus 1 over 3. And now that x over 3 can be rewritten again. And I'll do this slow. A lot of you could probably do this in one step in your head, and that's fine. I'm going to write this as, let's see, I'll write it as 1 over 3 times x over 1 plus 1/3. When you multiply fractions, you multiply their numerators and you multiply their denominators. Except I don't need to write it as x over 1. I'm just going to write it as x. So 1/3 x plus 1/3. So there it is. There it is in slope-intercept form. There's your slope. There's your y-intercept. Beautiful. Let's see how that matches when we take a look at the graph. So I'll shut that one off, turn that one on. And you do have a positive slope that is from left to right. It's increasing. Y-intercept, there's your decimal of 1/3. I'm trying to think if there's a couple friendly points you could try and calculate the slope from. Probably this one right here at -4 and -1. And I'd pick another one up here at say 2 and 1. If you find the slope of the line between those 2 points, you'll see that it's 1/3. All right, doing good out there. Let's try some more here. Kind of a friendly one that you're going to see in your homework is example C. So let me switch over here to example C, show you what that one's about. Let me take a look at it here first. So we've got a linear function, r of t equals -1/3 t plus 6, and it says choose the graph. Now they do something here that I'm not going to make you do, and it just doesn't really feel like you need to. That is, make a table of values and sketch the graph. Now, if this is a test, you want to get through this problem as fast as you can. So let's see about doing it on the quick. That's too much. So here's our equation, and I want to point out a couple things about this. The first thing I want to point out is that the slope is negative. Yeah, do it that way, -1/3. So what does that mean? That means as you look at the function, as you move from left to right, the line should be decreasing. So, okay, that allows us to eliminate a couple possibilities. So let's take a look here. As you move from left to right, this line is increasing. So I can eliminate this. That can't be one of my choices. I can also eliminate this one. That can't be one of my choices because that has a positive slope. All right, good. So now if I had to guess, I'm at least down to a 50-50 chance between these two graphs. This one and this one. Let's take a look at the other thing. The other thing is that the y-intercept is 6. Well, the y-intercept here looks like it's -6. So I can eliminate that one. Let's just check if this last one seems to fit everything we're looking for. Well, it's a decreasing line and the y-intercept is 6. So that one's our winner. Beautiful. You don't even have to refresh on WebAssign to try and get another try. You can get that one right the first time. All right, just a couple more here. Example D. Weather balloons are filled with hydrogen released at various sites to measure and transmit data about air conditions, about conditions such as air pressure and temperature. A weather balloon is filled with hydrogen at the rate of 1/2 cubic foot per second. And initially the balloon has 4 cubic feet of hydrogen in it. Find a linear function V that models the volume of hydrogen in the balloon at any time t. Wow. Sorry if that was kind of lengthy there. Let's see if we can't come up with some linear models. So let's go back over to here. Our linear model is going to have 2 things. V of t is going to equal m times t. Remember, this is supposed to be some function of time. Volume depends on time. Plus your initial amount. I'll call it b. Now the m, the slope, is the rate at which this is being filled. So that rate is 1/2 cubic foot per second. So this is going to be 0.5 T plus how much is in there initially. And how much is in there initially to start with is 4 cubic feet. So there's your model. V of T equals 0.5 T plus 4. Beautiful. Half of this is down. The second part is, if a balloon has a capacity of 16 cubic feet, how long does it take to completely fill the balloon? Okay. Well, that 16 cubic feet has to go into my equation someplace. And if you're thinking about it carefully, that 16 is really the volume. And you're looking for the time, right? So we're not going to be substituting anything for time. We're substituting for the volume. So it's going to be 16 equals 0.5 T plus 4. If I subtract 4 from both sides of this, I end up with 12 equals 0.5 T. Let me write that as 1/2 T, just to try and motivate our next step. And our next step is to solve for T. Next step was we want to get rid of that 1/2. And the way to get rid of that 1/2 is to multiply by the reciprocal. It's easier to think about the reciprocal as a fraction than it is as decimal. That's why I changed this over. So what's the reciprocal of 1/2? It's 2. So if I multiply both sides by 2, 2 times that gives me 24 equals T. Of course, that's going to be in seconds. So 24 seconds to fill up that balloon. Nice, nice. 2 more examples. We'll do this one. Then we're going to go back and take a look at what started this all, which was our roller coaster problem, and see if we can interpret the equation we get there. Lynn and Brianna are avid mountain bikers. On a spring day, they cycle down straight roads with steep grades. The graph gives a representation of the elevation of the road on which each of them cycles. Find the grade of each road. That's really the slope. Slope. That's what they're looking for. And I'll do these in different ways. So one way to do this is if you have a couple points. And those points would be this one here, which I can see clearly is on the y-axis, 0 and 1200. This other one, we kind of have to think about a little bit. And that's because you've got these tick marks that we're not really sure where that one is. But if you look here, here's one at 10,000. Here's another one at 14. There's 1, 2, 3, 4 tick marks that separate these things. So that means each tick mark is 1,000. If that's a tick mark of 1,000, then that point there is 15,000. And of course, 0 for Y. So with those 2 points, hey, we're in good shape. Call that your X1, Y1. This is your X2, Y2. The slope of the line is going to be 0 minus 1,200 divided by 15,000 minus 0. So negative 1,200 over 15,000. And we can simplify that if we want. Probably should simplify it a little bit. One little trick is you can cancel off trailing zeros and end up with negative 12 over 150. Probably want to take out your calculator at this point, maybe, or you can notice you can at least divide this by 3 and end up with negative 4 over 50, or a negative 8% grade. Negative 0.08%. So pretty steep. In fact, if you're out in Colorado or someplace like that, driving around on with an 8% grade, there's going to be signs that say, you know, caution, steep grade ahead, and they'll have a truck showing the grade here. 8% would be really steep. Now, a more practical way to do this is just to calculate two things. I need to calculate the rise, and I need to calculate the run. So that's probably the way I would do it for myself. The one thing you got to be careful about is that the rise is negative because you're going down. You're losing 600 feet in elevation over the course of 10,000 feet. So a little bit less than 2 miles. So that's going to be -6 over 10, which is negative 0.06. So my Lynn was running on the, or riding on a steeper road here. In any case, those are your two slopes. Beautiful. Let's go back to what started us all and take a look at an equation we can get from there. So that was our roller coaster data right here. Nice thing about this software is that I can actually fit an equation to this, and there it is. This is what's called the least squares regression. That's something you learn in statistics. You don't have to worry about that. But what it's telling me here, it's giving me an equation. Let me see if I can't write that down for us. And we'll look at it and see if we can interpret it. So the equation is our top speed. So I'll call that our y. Y equals 0.25205 x plus 34. So let's see if we can interpret that, at least part of it. So keep in mind that this is our top speed, and x is how far you drop. And what this is saying is that for every extra value of x, for each additional foot high that you build your roller coaster, your top speed is going to increase by this much, by 0.205 miles per hour. So that's pretty cool. Now this 34 is just kind of an artifact of the way it works when you fit an equation to some data. It's just going to try and find the best fit. It's not going to try and make this something you can necessarily interpret very easy. I guess one way to think of this is by building the roller coaster, you're at least going to go 34 miles an hour. That's the minimum that you want to go. And beyond that, for every foot of height you add to that initial hill, you're going to gain about 0.205 miles per hour. Pretty neat. Hope you enjoyed this section. Hope it's quick and easy for you. Good luck with it.